This is your presenter Asloob Mudassar, and I am presenting slide number 142 of the course on laser physics. This is actually a part C of slide number 142. Earlier, I have presented slide number A 142A and 142B. And this presentation, the today's presentation is in continuation of the previous two slides. I would suggest that you go through the previous two slides to understand this presentation. So here I am presenting solid state laser, and the type of laser that I am presenting is the Nd-YAG laser or Nd-doped YAG laser. Nd stands for neodymium and YAG stands for yttrium aluminum garnet. The electronic configuration of Nd in reference to the xenon is, this is the electronic configuration of xenon and extended to 4F4, 6D0 and 6S2. So this is the complete electronic configuration of the neodymium. And in reference to the krypton, its electronic configuration can be written as electronic configuration of krypton, along with we have 4d10, 5s2, 5p6, 4f4, 6d0 and 6s2. So I have given the neodymium electronic configuration in terms of xenon and in terms of the krypton. Now, two 6s electrons and one 4f electrons. So total of 3 electrons participate in the ionic bonding during the formation of the Nd-YAG. After the formation of Nd neodymium triply ionized ion, that is Nd3 plus ion, there are 4f electrons left, which are screened by 8 outer electrons, 5s2 and 5p6. These 8 electrons screen the nuclear charge. The crystal field is weak and does not influence the splitting of energy levels. The 4f electrons interact with each other and the energy splitting is governed by the Russell-Saunders scheme, normally abbreviated as RS scheme or RS coupling. In energy levels of interest, the 3f electrons have parallel spins with the total spin capital S is equal to 3 half. So each electron has a spin of half. Since these three electrons have parallel spins, so their spins will add together. So you have 1/2 plus 1/2 plus 1/2 amounting to 3/2. So the total spin quantum number capital S is equal to 3/2. For the 3f electrons, the orbital quantum numbers are, for the first f electron we have L is equal to 3, for the second f electron we have L2 is equal to 3, for the third f electron we have L3 is equal to 3. So L1 is equal to 3, L2 is equal to 3, L3 is equal to 3, corresponding to 3 f electrons. Many combinations of the total orbital angular momentum quantum numbers are possible, but the total quantum numbers of interest are capital L is equal to 0 with term symbol capital S, capital L is equal to 3 with the term symbol capital F, capital L is equal to 5 with the term symbol capital H, and when capital L is equal to 6, the term symbol is capital I. The total angular momentum quantum number capital J, which is given by J is equal to mod of L plus minus capital S, has many combinations. That is, many states are possible, but only those states which are relevant to the lasing process are shown in figure 142.2. Before I move to this figure, I want to explain that what is capital L is equal to 0, capital L is equal to 3, capital L is equal to 5, and what is capital L is equal to 6. You see that I have the 3 electrons which contributed to give you total spin capital S is equal to 3 half. And the angular momentum, angular orbital quantum number of each of the F electrons, because we are talking about 3 F electrons and each F electron has L is equal to 3. The second F electron has L2 is equal to 3. The third F electron has L3 is equal to 3. And the total orbital angular momentum quantum number will be given by the addition of these or individual quantum numbers. For example, you first need to add L1 and L2. And L1 and L2 can be added in the form of a mod. So mod of L1 plus minus L2. That is 3 plus minus 3, the mod of 3 plus minus 3. And you know that when you will add them together and subtract them together, you will get many values of angular momentum. Those resulting values will be added to the value of L3 in the form of a mod. For example, like the one that I have given for the mod of capital L plus minus capital S. Similarly, when adding L1 and L2 in the manner of mod of L1 plus minus L2, the resulting values are then added with the mod of resulting values plus the values plus minus the values of L3. And then you see that you will get the resultant values which will be denoted by capital L. So many values of capital L are possible. And here I had mentioned only some values of capital L which are of interest to S, which are of interest to the Nd-YAG laser. For example, capital L is equal to 0. The spectroscopic term corresponding to capital L is equal to 0 is the capital S, and corresponding to the total orbital angular momentum quantum number capital L is equal to 3. The symbol corresponding to that one is capital F, and corresponding to L is equal to 5, the term symbol is capital S, and corresponding to L is equal to C, the term symbol corresponding to this one is capital I. Now we have we have chosen these values. L is equal to 0, L is equal to 3, L is equal to 5, L is equal to 6, because these values are most relevant to our Nd-YAG lasers. So we have ignored the other values and we have chosen only these values. L is equal to 0, L is equal to 3, L is equal to 5, L is equal to 6. Now these values will be added to the total spin quantum number, which is capital S is equal to 3 half. So these values will be added to produce the total angular momentum quantum number capital J. So capital J is equal to mod of capital L plus minus S. So you will put the value of capital L one by one, keeping this capital S is equal to 3 half as calculated earlier. So trying different values of L over here, for example, L is equal to 0, then you will calculate J value, then put L is equal to 3, you will calculate J values, then putting L is equal to 5, you will calculate J values, then putting L is equal to 6, you will calculate J values. And with all these, you need to keep capital S is equal to 3 half, which is the total spin angular momentum quantum number. And you see that many values of J will then be possible. So capital J will have many combinations. That is, there are many states possible, but only those states which are relevant to the lasing process are shown in figure number 142.2. So let me show you this figure first. This is the figure. And the caption of the figure is selected energy levels important for neodymium doped YAG laser or Nd-YAG laser. On the leftmost you have these absorption bands. The first two bands have been shaded with gray, and the higher bands are empty, shown in white. These are the higher absorption bands, and the lowest two bands are shown. And the spectroscopic terms corresponding to these bands are, for example, to the lowest band, the spectroscopic terms are 4F5 half and 2H9 half. And to the next absorption band, which is shaded, the spectroscopic terms corresponding to this band are 4S3 half and 4F7 half. And you see that I have shown these wavelengths 0.73 micrometer, which is the wavelength of a pumping system, and zero point 0.8 micrometer is another wavelength of the pumping system. These two wavelengths are used as a pumping wavelength in order to pump the two absorption bands. And the lowest, the ground state of this system, that is the Nd-YAG system, is 4I9.5. So this is the lowest ground state, 4I9.5. And the higher and the state from which the lasing action will take place, that is the upper laser level, will be 4F3.5. And 4F3.5 will be split into two levels, R1 and R2, whereas the intermediate level, which is 4I11.5, will be split into six levels. So these levels will be explained. And the wavelength that is emitted from the through the transition from 4F3.5 to 4I11.5 will be 1.06 micrometer. And you know that these the numbers have also been shown in centimeter inverse, which is 1 over lambda. And you see that this level corresponds to an energy which is nu over c is equal to 1 over lambda, and this 1 over lambda corresponds to 200 centimeter inverse. And the energy levels of the other levels have also been shown. For example, when this level 4I11 half will split into six levels, the lowest level will have an energy corresponding to 2001 centimeter inverse, and the uppermost out of these six levels will be 2526 centimeter inverse. You see that I have drawn 2001 centimeter inverse below the level of 2000 centimeter inverse, because in order to make use of the space properly. Otherwise, this 2001 centimeter inverse will lie above this 2000 centimeter inverse level. And you know that these R1 and R2 levels, which are the splitting of 4F3.5 levels into two levels, R1 and R2, they are corresponding, they have corresponding values equal to 11,414 centimeter inverse and 11,502 centimeter inverse. So you see that this level, which is 4I11.2, is split into six levels in the presence of the electric field, or due to the Stark effect. Similarly, this 4F3.5 level will be split into two levels under the application of the electric field. So we are not talking about the other higher absorption bands, because these two bands will be enough, and these two bands will decay non-radiatively, and through a fast decaying process these will decay to the level 4F3.5 level. So this 4F3.5 level will form an upper laser level for the case of the Nd-YAG laser. And of course, from this level, the transitions can occur to 4I11 half and 4I9 half. So the transitions from 4F3 half can occur to the lower levels and will emit different wavelengths, which we shall be talking about in the subsequent paragraphs. The lower states are 4I9 half, 4I11 half, 4I13 half, etc. This level, which is 4I13 half, has not been shown in the diagram. Out of these three, 4I9 half, being the lowest in energy, acts as the ground state of the Nd-YAG. The upper laser level is 4F3 half. There are some bands lying above in energy than 4F3 half. Only two most important bands used in pumping process are 4F5 half, 2H9 half. This corresponds to the first absorption band, and the second absorption band corresponds to the term energies, which is 4S3 half and 4F7 half. The capital L is equal to 6 and capital S is equal to 3 half. Give the following values. For example, with the capital L is equal to 6 and capital S is equal to 3 half, you can put these values over here to calculate the total value, total quantum number J. And the total values and the J will have the following values: 5 half, 13 half, 11 half, 9 half. So these are the J values. And you know that J values are written in the form of the subscript. For example, 9 half is the J value, 11 half is the J value, 13 half is the J value. So these are the J values that result when capital L and capital S are combined together to form the total angular momentum J of the system. So I can write the possible terms in the form of 4i, 15 half, 13 half, 11 half, and 9 half are the required states. So when capital L is equal to 6 and capital S is equal to 3 half, the possible states will be 4i, 15 half, 13 half, 11 half, and 9 half. So these will be the required possible states. Only 4i 9 half and 411 half have been shown in figure 2. So you can see that I have shown only these two levels, that is 4i 9 half and 411 half have been shown. The other levels have not been shown because these two levels are important as far as the Nd-YAG laser is concerned. Each level is 2j plus 1 fold degenerate, and the degeneracy is lifted, that is the levels get splitted into 2j plus 1 sublevels when the magnetic field is applied. So you see that each level is actually 2j plus 1 levels, and all these levels have the same energy. So that's why we call them as degenerate levels. And when we apply the magnetic field, each level will be split into 2j plus 1 levels under the application of the magnetic field. But under the application of the electric field, if electric field is applied, which is the case of the Stark effect, if electric field is applied, then the levels minus j and plus j will be degenerate. That is the level with the values minus j and with the value plus j will form the same level, will be a same level. So the levels with the minus j and plus j will have the same energy. That is, each level will be doubly degenerate. So doubly degenerate mean that the level is one, but actually these are the two levels which are coincident with each other, having the same energy. So they are not visible as separate levels. So these are the doubly degenerate levels under the application of the electric field. That is, under the application of the magnetic field, the levels are split. The levels are split into 2j plus 1 levels, and so under the application of the electric field, the levels will be 2j plus 1 divided by 2, because minus j and plus j will be degenerate levels having the same energy. So 2j plus 1 divided by 2 will be the total splitting of each level under the application of the electric field. Let us consider 4i 11 2 level with j is equal to 11 half, which j is equal to 11 half or 11 by 2. Under the application of the magnetic field, the magnetic quantum number has the values. So mj is the values of the magnetic quantum number under the application of the magnetic field, and when capital J is 11 by 2, then under the application of the magnetic field, this capital J will have the following values, and which we call them as mj values. So mj values will be 11 half, 9 half, 7 half, 5 half, 3 half, 1 half, and minus 1 half, minus 3 half, minus 5 half, minus 7 half, minus 9 half, and minus 11 half. So these are all the values will be possible as mg values under the application of the magnetic values, under the application of the magnetic field, and these will be the values of the magnetic quantum numbers. That is, the level 4i 11 half will be split into 12 levels, because these are the 12 possible values. Now consider the application of the electric field only. The possible values of Mj, that is the electric quantum numbers, that is the quantum numbers due to the application of the electric field will be Mj is equal to mod of plus minus 11 half, mod of plus minus 9 half, mod of plus minus 7 half, mod of plus minus 5 half, mod of plus minus 3 half, and mod of plus minus 1 half. Because under the application of the electric field, the levels are doubly degenerate. That is the plus J value and the minus J value will have the same energy and will form only a single level. So these levels are the doubly generate under the application of the electric field. That is the level 4I 11 half will be split into 6 sub-levels under the application of the electric field. These sub-levels have been shown in figure 2. So here you can see that the 4I 11 half level has been split into 6 sub-levels under the application of the electric field. And this could be the application, and this electric field could be due to the addition of the Nd-YAG and the triply ionized ion in the host material, which is the YAG material, and due to that one the electric field may appear around such sites, and the levels will be each level, that is the I11 half, will be splitted. Or externally, you can also apply the electric field externally to make these levels to be split into these 6 levels under the application of the electric field. So I have shown over here only that 4I11 half will be split into these 6 levels, 6 sub-levels. Each sub-level is doubly degenerate. That is the plus J value and the minus J value have the same energy. In the present description, we are considering each sub-level as a singly degenerate or simply as a singly non-degenerate level. So you see that here we are treating these 6 levels, although each level is actually a 2 level having the same energy. So we are treating these 6 levels as a doubly degenerate level. So these are you can also treat these 6 levels as single levels, single non-degenerate levels. There are many absorption bands above the upper laser level, which is the 4F3 half level, but only 2 bands. The first absorption band having terms of 4F half and 2H9 half, and the second absorption level having term symbols corresponding to that are 4S3 half and 4F7 half are more important. So the 2 absorption bands which I have shown in the figure and shown in the dashed, for example, these 2 levels are the important levels as far as the lasing process in the Nd-YAG laser is concerned. Pumping is done to these 2 bands which non-radiatively decay to a strongly coupled 4F3 half level. The decay from 4F3 half to the lower laser levels, for example 4I 15 half, 13 half, 11 half, 9 half, is normally electric dipole forbidden under delta J is equal to 0 plus minus 1. So these are the only, and due to the field of the crystal, the transition delta J is equal to 0 plus minus 1 are weakly allowed. So you see that under the selection rules allowed values of delta J should be 0 plus minus 1. And these are the electric dipole forbidden values. That is the transitions should not obey these values. That is delta J is equal to 0 plus minus 1 should not be obeyed. That is why we are calling them as electric dipole forbidden transitions. But you know that there, due to the impending of these in the field of the crystal, the transition delta J is equal to 0 plus minus 1 are weakly allowed. There is a large gap between F between 4F3 half and the levels below it. Thus, the population from the two absorption bands accumulate in the 4F3 half levels, which act as the upper laser level, as the decay rate of 4F3 half is very large, with a lifetime of this state is of the order of 230 microsecond. So let me read again. The decay from 4F3 half to the lower laser levels, which are 4I15 half, 13 half, 11 half, 9 half. Out of this, I have shown only two levels, 11 half and 9 half has been shown in the figure. You can see there that I have shown only 4I11 half and 4I9 half have been shown. Only these two levels have been shown. So the decay from the 4F3 half to the lower laser levels 4I15 half, 13 half, 11 half, 9 half is normally electric dipole forbidden under the transition that delta J is equal to 0 plus minus 1 do not allow these transitions to take place. And due to the field of the crystal, the transition under delta J is equal to 0 plus minus 1 are weakly allowed. There is a large gap between 4F3 half and the levels below it. Thus, the population from the two absorption bands accumulate in 4F3 half levels, which act as the upper laser level, as the decay rate of 4F3 half is very large and the lifetime of this level is approximately 230 microsecond. So you see that through the pumping process, the pumping is done to these two absorption bands. And these two absorption bands decay very quickly to the 4F3 half levels, because the other levels are at a very large distance below it. So the transition from these absorption bands will only occur to this 4F3 half level. So this 4F3 half level gets very much populated and forms the upper laser level of the Nd-YAG laser system. The transition for 4F3 half to 4I11 half is the strongest among the other lower 4I levels. 4I11 4I11 half differs in energy from 4I9 half by 10 kT, that is 10 times its thermal energy, and 4I11 half decays non-radiatively to 4I9 half in a very short time of the order of 100 picosecond. Thus, the level 4I11 half is almost empty, as the level 4I11 half and 4I9 half attain thermal equilibrium very shortly. The laser transitions R1 and R2. These two R1 and R2 lines thus resemble a four-level laser system. Because you know that in the four-level laser system, the lower laser level is almost empty, and the same case also appears over here. Because this level, which is the 4I11 half level, decays very quickly to 4I9 half level. And so the population in this level, which is the 4I11 half level, is almost empty. So this level is almost empty over here. So this is the 4F3 half is the upper laser level. 4I11 half is the lower laser level, which is almost empty due to the non-radiative decay to the 4I11 half. So this actually resembles the four-level laser system. The laser transitions R1 and R2 thus resemble a four-level laser system. The R2 line will give you a wavelength of 1.064 micrometer, has the highest stimulated emission cross section, for which the Nd-YAG laser is famous. You can see this 1.064 micrometer wavelength, which is emitted from the R2 transition. That is the transition from the R2 level to the 4i 11 half level. So from R2 to transition from R2 to 4i 11 half level will give you 1.06 micrometer wavelength, and this is the strongest wavelength of the Nd-YAG laser and is the most popular wavelength. The wavelength 1.319 micrometer can also be made dominant in the transition from 4f3 half to 4i13 half. You see that this level 4i13 half, I have not shown this level, but the transition 4f3 half to 4i13 half will take place, will give you a wavelength equal to 1.319 micrometer provided. So this wavelength can be selected provided the cavity mirrors have multi-layer dielectric coatings, which enhances the refractivity of 1.319 micrometer and suppresses 1.064 micron. The transition, so thus this wavelength 1.319 micrometer can be selected. The transition from 4f3 half to 4i9 half, giving a wavelength of 0.946 micron, can also be made to occur under pumping with a suitable diode, for example aluminium gallium arsenide laser. So this transition, that is 0.946 micron, can be obtained through the transition from the 4f3 half to the ground state, which is 4i9 half. So that is a transition from R1 level to 4i9 half level. So when this transition will takes place, it will give you a wavelength of 0.946 micron. But for that one, you need to use a pumping technique, pumping source as aluminium gallium arsenide laser, because this source will then pump the R1 level only. So this R1 level will be pumped, and the population the population inversion will be achieved for the R1 level, and then R1 level will decay to 4i9 half level, and then will emit 0.946 micron wavelength. These transitions are homogeneously broadened at room temperature due to the interaction of these transitions with lattice phonons. At lambda is equal to 1.064 micron, delta nu, that is the width of that line, is nearly 4.2 centimeter inverse. And in terms of frequency, it is 126 gigahertz at room temperature. Due to a large lifetime of the upper laser level, Q switching operation is easily implementable. So since the upper laser level has a very large lifetime, so Q switching operation can be very easily implementable. Nd-YAG laser in mode locked operation gives pulses as short as a few picoseconds. Both CW, that is the continuous wave, and pulsed operations are possible. Xenon lamps with a pressure of 1000 torr are used in pulsed pumping, and krypton lamps with a pressure of 5 atmosphere are used in CW operation. Typical active medium rod diameter is of the order of 5 millimeter and length of the order of 10 centimeter. Active medium in slab configuration reduces thermal birefringence and thermal lensing effect. These two things have been discussed in some previous slides. With the flash lamp pumping, the slope efficiency is about 3%, And the slope efficiency has been discussed also in much greater detail in one of the previous slide. So the slope efficiency is about 3% for CW, and pulsed operation with the average power ranging from 1 to 5 kilowatt. With the diode pumping, the slope efficiency is greater than 10%. For longitudinal pumping, the average power goes up to 15 watt, whereas for transverse pumping, the average power goes up to 100 watt. So you see that the Q switching operation and the mode locked pulses can be very easily obtained from the Nd-YAG laser. Q switching, because the upper laser level has very long lifetime, and the mode locking operation because the line width of each wavelength which is emitted is very wide. Application area is quite diversified for the Nd-YAG lasers. In laser rangefinders and in target designators, Nd-YAG in Q switched mode has been used with pulse energy ranging from 80 to 120 millijoule. Pulse length from 5 to 25 nanosecond, and with pulse repetition frequency up to 20 hertz. In medical field, CW laser is delivered using optical fiber delivery system to reach internal organs including stomach, bladders, lungs, etc. Secondary cataract is treated using Q-switched Nd-YAG laser. Optical power varies from organ to organ. A pulsed Nd-YAG laser with average power from 50 to 100 watt, with pulse energy from 5 to 10 joule, with pulse repetition from 10 to 100 hertz, can be focused on materials for drilling purposes. The beam focus is adjusted according to the diameter of the required hole size. In welding, the beam is conveyed to the workplace through fiber optics with adjustable beam diameter from 0.5 mm to 2 mm. The beam delivery system makes the Nd-YAG laser system superior over the CO2 laser system as far as the welding is concerned. So the next I shall be presenting Nd glass laser. And this is the end of slide number 142 and part C of this.